Hello and welcome back to another Project IB45 video, and this time we'll be covering fluid resistance, which is a topic for both HL and SL physics. So first, what is a fluid? Basically, a fluid is a substance that can flow. Both liquids and gases are considered fluids in physics. So what is fluid resistance? Fluid resistance is a force that opposes motion through a fluid, and this can also be called the drag force. The explanation behind this is that as an object moves through a fluid, particles will collide with the object, and these collisions create a resistive force that slows the object down. There are a few factors affecting fluid resistance. The first one is speed, and the faster an object moves, the greater the drag force because there are more collisions happening between the object and the fluid. The surface area also affects fluid resistance, so a larger surface area creates more resistance. Shape also plays a part in affecting fluid resistance, as streamlined shapes reduce drag. And also fluid density, as denser fluids create larger drag forces because there are more particles in the same volume. And finally, viscosity. More viscous fluids resist motion more strongly. So here are some graphs of a skydiver. In the first graph, we'll be looking at distance and time. So this graph shows the skydiver's distance fallen over time. And notice at time 0, the gradient is completely flat. It's like if you draw a tangent, it'll be completely flat. And that's because the initial velocity is 0. As the skydiver accelerates, the curve bends upwards because the velocity, which is the gradient of the graph, is increasing. So eventually, once terminal velocity is reached, the velocity becomes constant. Therefore, the curve turns into a linear line with a constant gradient. Next, we can talk about velocity. So this graph tracks the skydiver's speed or velocity in a given direction. And at the start, the gradient is at its steepest when the skydiver first steps out of the plane. And this is equal to acceleration due to gravity. As the skydiver speeds up, air resistance increases, which causes the curve to flatten out. And finally, the curve reaches a horizontal asymptote, which is this dotted line over here. And this terminal velocity happens when the resultant force is 0 because the force caused by the fluid resistance and the force due to gravity are equal. And finally, we can look at acceleration versus time. And this graph shows how the skydiver's acceleration changes. At the moment of the jump, velocity is 0, meaning that there is no air resistance, so acceleration is at its maximum of 9.81. As the skydiver falls faster, the upward drag force grows, reducing the net downward force. Consequently, the acceleration drops continuously, following over here, which you can see from the downward slope. When the skydiver hits terminal velocity, the forces balance perfectly, and the acceleration drops to exactly 0, which is seen around here. So here's a small question about fluid resistance. So this question is about projectile motion. They often come hand in hand. A ball is kicked at an angle to the horizontal. The diagram shows below shows the position of the ball every 0.5 seconds, so 0.5 whatever. On the y-axis we have vertical displacement, and on the x-axis we have horizontal displacement. The acceleration of free fall is g equals 10 meters per second. This is just on the diagram above. Draw a line to indicate a possible path for the ball if air resistance were not negligible. Basically, this is what it would look like. So when air resistance is included, it changes our perfect parabola, which is over here, in 3 key ways due to a continuous loss of energy. So as you can see that there is a lower peak. Here's the peak of the original curve, and now here's our peak, the new one. So air resistance constantly opposes vertical motion, meaning that the ball cannot rise as high, and therefore this peak will be well under the peak, this value of 31 meters. And also, this ball will have a shorter range, as air resistance acts horizontally against the ball's motion, slowing its forward progress. And the ball will hit the ground much earlier, well before the original 40-meter mark here. And also, due to air resistance, there will be an asymmetric shape. Because the horizontal velocity drops continuously throughout the flight, the ball falls more steeply than it climbed. So here you can see the gradient here is less than here, and this shifts the peak of the curve to the left of the original center, creating an asymmetrical skewed path.